Okay, yeah. So we ended with last time with the theorem, whoops, which is what essentially told us that the space of square integrable functions with our inner product is complete. All right? And this particular example of a space of functions is well known. It's called Hilbert Space. Now I have to admit, you get pretty famous when you get a space named after you. Minkowski space, Euclidean space. Part of my actually part of my postdoc research was trying to get a space named after me. I actually didn't want it to be named after me, we just wanted to give it its name. So we ended up calling these spaces monadrofolds.
Did you make a song for that?
Huh?
Didn't you make a song for that?
We did make a song for it. We performed it live at a gong show. Anyway, that's another story. At any rate, our name never really took off. They never took monadrofolds as a solid. I mean, the spaces themselves were interesting. They just called them asymmetric orbifolds, but monadrofold is a way better title. At any rate, you've all heard and probably used Hilbert spaces. But there you go. That's what we've been working with this minor definition of a space of square integrable functions, which, as we proved last time, is actually a complete space. Now, this of course means that we can define orthogonality, normalization, and orthonormality with the inner product we identified. So if I have some functions, fi and fj, then using the inner product, oh goodness. If the result of the inner product of the functions is the Kronecker delta function, delta ij, then this tells me that the set fi is orthonormal. Okay, so that's our working definition of orthonormality. However, we will expand it a bit. We won't do it anytime soon, but we will do it later. We were studying special functions. But we could, instead of identifying this as our inner product, we could just as well identify our inner product as something remarkably similar. Except there's a weight function included in the definition. Okay? That's what the W there stands for. The weight function is the same no matter which two functions you're inner producting. Okay, so this is a universal thing in the definition of the inner product. Okay? And again, we'll actually use this a bit later on.
Does
So,
this change your space? Sorry, should have raised my hand.
no, go for it.
Does that change the space we're considering? Changing that product?
It changes. Let me think. I am not sure if it would actually change the content of the space. When you're referring to the content of the space, you're referring to the functions that live thereon. Okay? There there's a possibility, but I'm not 100% sure if it would actually change the content of the space. It obviously changes the structure of the space because the inner product is changed.
Yeah.
But whether it changes the allowed functions is still, I'm not 100% sure about that.
Okay, that's fine.
Okay?
Thanks.
Let's look at a set of orthonormal functions. For example, you've probably seen these before. What are they called? Do remember that normally our inner product and this specification of square integrability is always over a range. Okay, so we have a range for x. We can take it to be infinity, but normally it's just got two bounds, a and b. So these functions over the interval pi minus pi to pi, these are called, oh come on guys.
Periodic square.
I've heard everything except the correct answer. But you all know this.
Looks familiar.
Yeah, it looks familiar. Hell yeah, it looks familiar.
Sinusoids?
Huh?
Sinusoids?
They're called Fourier functions.
Oh,
there we go.
Ouch.
That's what it is.
Yeah. Obviously.
Look at that, two F's in the name. Well, I called it, no, it's not why I called it that. I'm kidding about that, but I like it. That's pretty good. Anyway. No, these are the Fourier functions. So let's very quickly review them. Let's see, if Fn, Fm, if I take the inner product of two of them which are different, so n and m are different, then this is the integral from minus pi to pi of Fn star, Fm, dx, which is of course 1 over 2 pi, integral from minus pi to pi, e to the I m minus n x dx, which is 1 over 2 pi I times m minus n, e to the I m minus n x from minus pi to pi, which is 0. Okay? The n and m here are integer labels. Okay, and then of course, if we take the same function and we take the inner product with itself, this just becomes the integral of e to the 0, which is of course the integral of 1. So we get the range 2 pi over 2 pi, and it's 1. Okay? So clearly these satisfy this orthonormality condition. Now there's a question of whether they form a complete basis in the space. And that is what we are now going to turn our attention to. Because like everything else, when you take the limit to infinity, things become way more tricky and subtle. Okay? So we've talked about that the space of square integrable functions is a complete space. I'm actually going to ask, Seth,
Yes.
what was the essential criterion that our functions had to satisfy in order to argue that they formed a complete set?
The Cauchy sequence can't tend outside of the space.
Exactly. Any Cauchy sequence cannot limit towards something outside of the space. All Cauchy sequences had to limit towards something in the space itself. Okay? Now remember, the function space is, it's a gazillion functions. I mean, there's functions have continuous parameters, so there's an uncountable infinite set of functions. Thanks for clarifying this with me this afternoon, Josh. Now what we want to talk about is a basis in this space. Now a basis is countable even though it might be infinite. you can still say this is the first basis vector, the second basis vector. So they can be indexed by some integer valued thing, and even though there's an infinite number of them, they're countable. They're countably infinite. Versus asking how many functions are there in the space. That's uncountably infinite. Okay? So we want to find a complete set of orthonormal functions, or we want to find the criteria that have to be met in order to evaluate that a set of orthonormal functions is itself complete. So here we go. All right. So here is a potential way to define a complete set. An orthonormal set of functions is complete if any function in Hilbert space can be expressed as a linear combination fx equals sum of I equals 1 to infinity, ci fix, such that the sum converges at every x. Okay? Now, this could be our definition. It could be something, but it's actually going to turn out to be not the right thing to say. Okay? First of all, notice this is a function evaluated at values of x over some interval from a to b. And all this is saying is pick a value of x. So if the interval goes from 0 to 1, pick a value of x equals 1/2. The function evaluated at 1/2, okay, should be converged to by this sum evaluated at x equals 1/2. That's what this is saying. At every value of x, this sum should converge to the function at that point. Okay? It turns out this is a bit strong. Okay? And if you think about it, doing a convergence at every point over an interval is likely to run into problems with interesting and special case functions like the Dirichlet function, which we talked about last time. The one where it's non-zero at isolated points. Okay? But those functions are part of Hilbert space. Okay? This definition is sort of, it's problematic when you encounter functions like that. So we need a more working definition. And so it turns out that we can modify the notion of convergence a bit. Turns out there are 3 versions of convergence. Version 1 is called Pointwise. Pointwise convergence says the following. A sequence of functions h n x, where n is just some integer value, integer label, converges pointwise to a function hx on the interval a to b if for every x on the interval and every positive parameter epsilon there exists an integer n which depends on the point in the interval that you're working with, so it depends on x, or it can depend on x, and of course it depends on the small parameter epsilon, such that for the index on the functions being larger than n gives rise to the magnitude of the difference of hx and hnx is less than epsilon. Okay? Now, the detail of this will probably make more sense when I give you the second definition, which is called uniform convergence. And uniform convergence looks remarkably the same. Yeah, I'll just have to write it up here. A sequence of functions h and x converges uniformly to h of x again defined on the interval from a to b if for every epsilon greater than 0 there exists an integer n depending on epsilon such that for n larger than n for all x on the interval. Okay? Anna.
What's up?
Hey, what's the difference in these two definitions? Can you see it?
Uniformly versus pointwise?
Yes.
So with uniformly, does that mean it just completely converges, whereas pointwise is it might converge like kind of scattered? Well, I don't know what pointwise means. I don't know if I've ever heard that before.
Okay, pointwise basically says that if you want to establish the convergence, you do it at each point x in the interval, and this integer n might be different for different values of x. Okay?
Okay.
For the uniform case, n only depends on the small parameter that you've chosen,
Yeah.
but this n will cover the entire interval, because this has to be true for every value of x in the interval, all at once.
Okay.
Okay? Now, here's a question. Does one of these imply the other? If you're pointwise convergent, are you automatically uniformly convergent? Or if you're uniformly convergent, are you automatically pointwise convergent? Who says 1 implies 2? Raise your hand. Who says 2 implies 1? Raise your hand. Oh, sorry, I didn't look up when you guys were voting on the first. Okay, well, I got a lot of hands up. Okay. Yeah, it turns out that 2 implies 1. So if something is uniformly convergent, it's automatically pointwise convergent, but not so the other way around. Okay? All right, so that's 2 interesting versions of convergence, neither of which are what we want. I know. If you think about it, though, this was kind of using something like pointwise or uniform convergence in this proposed criterion for completeness. Yes?
What's the point of big N?
Of baby n?
The big N.
The big N?
Yeah, just looks like a function that has to be less than little n, and I'm not sure why that matters.
It's an integer.
I imagine it matters, but I can't tell why yet.
What does it do to x and epsilon?
I mean, so
Is there a reason the index little n has to be bigger than big N?
well, no. The thing is that it's that only for n larger than this big N is this true.
Okay.
So n is sort of the speed limit. It's the speed limit, and if you're going less than n, then the difference between the function you're trying to converge to and the point in the sequence which you are could be larger than epsilon.
So if I was trying to use the series of, or the sequence of like the Fourier sequence, what would I choose for big N?
It depends on what you pick for epsilon.
Okay.
That's why n depends on epsilon.
Okay.
Okay, so if I pick epsilon, so if I have 2 values of epsilon, epsilon equals 1/2 and epsilon equals 1, which one of these has a correspondingly larger big N?
Probably the 1/2.
Yeah, the 1/2. What about epsilon equals 0.0001? You're making n bigger.
Is there like an accepted way that most people build that, or
That most people what?
build n of x and epsilon? Because right now it just feels like I could just make it something, where if epsilon got smaller, it got bigger,
Yes.
and that's it.
Yeah,
Oh,
that's it. The difference, though, is that here you're going to have to do it at each point x. And you could have, for a given value of epsilon, you can pick one epsilon and say, I want everything to be smaller than epsilon. You might actually have to pick your n's to be different at different points.
okay.
But here, if the sequence is uniformly convergent, you can always, for a given value of epsilon, find a n which will apply to every x.
Okay.
Okay? All right. So, it turns out that we need yet another. So finally, we have convergence in the mean. A sequence of functions h and x converges in the mean to hx on AB if for every epsilon there exists an n epsilon, okay, such that for n greater than n, Now you'll notice every damn thing I wrote is exactly like in uniform, right? So clearly, if in the mean is going to differ from uniform, I've got to write something different here. Okay? Here's what we're going to write. The integral from a to b of the magnitude of the difference between hx and hnx squared dx is less than epsilon. Okay? Now, does 2 imply 3 or does 3 imply 2? Who says 2 implies 3? Who says 3 implies 2? 2 actually implies 3. 2 is the strongest of these in terms of specifying a level of convergence. 1 and 3 are just sort of disconnected from each other. 1 doesn't imply 3, neither does 3 imply 1. Okay? This is what we're going to have to use in order to be able to handle things like the Dirichlet function. Okay? Because remember, the Dirichlet function itself as a function is fucked up. You know, there's these points which are non-zero, but they're only over, you know, values of x, you know, which are separated from each other. However, the integral, or with the Dirichlet function, is nice and smooth, right? It's 0, exactly, okay? So if you're trying to compare functions themselves, the Dirichlet type, those that are almost 0 are going to screw you up. Whereas here, because of course this is the Lebesgue integral, everything will work out smoothly. Okay? All right. Now, a very important observation from these two types of convergence, which will be useful later on, is that hx equals the limit as n goes to infinity of hnx. Okay? That's sort of the end of these stories, all right? Because if you take n to infinity, then you can take epsilon to 0, and these differences are just 0, okay? However, for 3, you're not guaranteed this, okay? Because this is functional, whereas this is integral. And what can be true under an integral doesn't necessarily correspond to a functional. Okay. Now, what the hell does all this have to do with the completeness of the basis? Well, now I can write the definition of a complete basis. So first of all, set hnx to be the partial sum okay, so this is a series, this is a sequence. Then for pointwise or uniform convergence, we have that hx equals the sum from I equals 1 to infinity of kix, right? That's what I just said earlier. And if you think about it, this kind of looks like a complete basis in the space. Okay? It kind of looks like a complete basis in the space, but this is what we're going to say, because remember, this kind of statement is encoding pointwise and uniform, and whereas we want to use convergence in the mean. So this is going to be our criteria. Let g of x be any square integrable function in Hilbert space and let fi be an orthonormal set of functions. Okay. If there exists constant coefficients which we might call AI, such that g and x, which is going to be defined as that superposition, converges in the mean to g of x, then the set fi is complete. Okay? So, so if this guy is converging to g of x, then we'll notate that, and this doing it in the mean, then we'll notate that as g of x is equal with a dot over it, the sum from I equals 1 to infinity ai fi x. Which is not g of x equals I equals 1 to infinity ai fi x. Okay? This is true for pointwise, uniform, or mean, whereas this is only true for pointwise or uniform convergence. Okay? Where, of course, what I mean by this is the limit as n goes to infinity of the integral from a to b of g minus the sum from I equals 1 to n of ai fi squared dx is 0. Okay? All right. So in trying to determine whether a set of orthonormal functions is complete or not, all we have to do is set up this sequence and ask, is that sequence going to converge in the mean to the function g of x? Okay? If it happens to converge uniformly, then yes, it's going to be complete. But it might not converge uniformly, and it still might satisfy this definition of converging in the mean. Okay? All right, now, we might wonder how, if I have this convergence, or this convergence, how do I extricate the coefficients in the expansion AI? Okay? Well, in this case, it's pretty simple. Obviously, AI is fi g of x. Since fi of j, since these are orthonormal. Okay? Here it's not as simple. So if you happen to have something which is converging pointwise or uniform, then in taking a function and expanding it in the basis, finding the coefficients of the expansion is rather straightforward. However, if you find something which is only converging in the mean, then finding the expansion coefficients can require a little bit more work. It's actually not that bad. Okay? So let's see what the coefficients are in this story. So I'm going to define, let me get rid of this. So I'm going to define a sequence Mn okay? This is for a given function g, and we're working with the set fi, and then the ai's are the coefficients that we want. Notice this is a sequence because we're only summing to n, okay? Now, this is positive definite, so Mn is greater than or equal to 0. And if this is positive, then the coefficients ai should do what to this value? It should minimize it. Okay? This is the difference. It's a positive number, and you want the difference between the sequence and the function to which it's going to converge. You want that to be a minimum, and that'll extricate the values of AI. Okay? So here we go. Let's expand this. Okay? And now let's clean it up. And here I've introduced terms fi and g. All right, is everybody following these steps?
I think so.
You think so, or
You're just doing the inner product.
say it again?
You're just doing the inner product.
Well, no, the first step was I just took this and I multiplied this thing by its complex conjugate, because that's what the magnitude squared is.
Yeah.
And then I distributed everything out and got these terms, and then I identified that this integral of this thing over dx was the inner product of g with g. Okay? And then similarly for the rest of them. Okay?
Yeah.
Where these c's are inner products. This is literally just arithmetic, not even algebra. Okay? All right, now, I want you to consider mn plus the sum from 1 to n of ci squared minus the sum from 1 to n of ci squared. Andrew, what's that equal to?
Zero?
No,
No, is it, oh,
it's an easy one.
is it just all that? The right side of that?
Is it what?
Is it,
mn plus,
oh,
this-
it's just equal to, and then.
yeah, it's equal to mn. Yeah, it's kind of like multiplying by the identity, that kind of shit, you know? Okay, all right. But we can rearrange this in the following form. Okay? Where remember, mn is greater than 0, it's greater than or equal to 0. Now we want to, we're trying to use this analysis to pick the values of ai which minimize mn. Well, where in here does ai appear? In the middle. This is a positive contribution, so if I want this to be its smallest possible, if I want mn to have the smallest possible value, what do I want each of these terms to be? Say it again?
You want it to be the same, so AI equals CI.
Yeah, I want these terms to be 0, so I want ai equals ci. Okay? Now that leaves us with g is greater than or equal to the sum from I equals 1 to n of ci squared, or the sum from I equals 1 to n of the magnitude of the inner product of fi and g. Okay? Now, if we take n, the upper limit in the summation, to infinity, does this change? Does the left side of this change if we take n to infinity? No, this is just the inner product of the function with itself. So what we can say is that g, inner product with g, is greater than or equal to the sum from I equals 1 to infinity of ci squared. Does that look familiar? Can anybody name it? Where would you have to look to figure that out?
So, in the definition of, our inner product space, we wanted that GG, the inner product, to be zero.
Right, right. Well, at this point, all I'm doing is I'm extracting the AI and then I'm getting to this result. And I'm asking you, what is this result called? Where have we seen this before? We've got a function, we've got a vector, and it's expressed.
It reminds me of quantum and probabilities.
So we're trying to figure out whether the basis that these CIs are defined with respect to, the FI, is complete or not. And in this case, we have these sequences which are converging to these functions, but nonetheless, here's the inner product of two functions, and its inner product is greater than or equal to the sum over this set of coefficients, which are derived from the inner product of the functions with the basis, with the set of orthonormal functions. We encountered this right after we introduced inner products. It's called Bessel's inequality. And the inequality part arises if this set is, or the set of Fi is,
Not orthogonal.
no, these are orthonormal.
The set is complete.
It's not complete. Remember? Do I need to remind you of this? I mean, look, if I have a vector, which is A I hat plus B J hat plus C K hat, and then, sorry. If I have a space, and my basis is only two-dimensional in the space, and I have a vector V, then V, and I'm going to use that shit notation that you learned with this. V dot V is definitely going to be larger than the x component squared plus the y component squared. Because V dot V will include the z squared. However, if the basis in the space is complete, then this is equal. Okay? Everybody on board? Okay, so this is just a repeat of Bessel's inequality. And so, we can use Bessel's inequality to determine whether or not the set of orthonormal vectors is complete, i.e. it forms a basis in the space. If this is subject to an equality versus an inequality. We can also, I know I'm going to regret erasing anything, but whatever. We can also write Parseval's equation in infinite dimensions. If Fi is a complete set of orthonormal functions, then for any G and H on the space, we have the G inner producted with H can be written as the sum from I equals 1 to infinity of G inner producted with Y, G inner producted with the Fi, and then the Fi inner producted with the H. and it's Parseval's equation. All right, both of them hold true for this lovely infinite dimensional case. All right. Any questions before we go on? Yeah.
Well, when we're working with vectors in finite dimensions, we can kind of give meaning to the, just taking out the fi and fi, of course, that'd be the identity, where you take essentially an outer product of two vectors.
Yeah.
Is there the same meaning to that in infinite dimensions?
So you're, okay, so let me sharpen this notation a bit.
Not the broadcat notation. So.
No, it is the broadcat notation.
I like the bracket notation.
Where we're using the fact that if this is a complete set, is that what you mean?
Yeah, and I'm asking, is there like can you understand what an outer product means in the, if you took those and they weren't just f's that make the identity, if they were arbitrary functions, does that mean anything?
I would say yes. Although I can't put a name to it. Yeah, I can't put a name to it. And I'll see what all you are laughing at. I think.
The completo.
Completo. Completo.
Completo.
Yeah, I have to think about that, Joel. Okay, other questions? Completo, that's my favorite new word. All right, so now we're going to take a slightly different look at the same point, that is figuring out when a set of orthonormal functions is a complete basis in the space, but we're going to do it from a different perspective. And this will end our careful analysis of the definition of Hilbert space with its inner product and all of its convergences and everything. And next time we're going to start with some functions. Okay? Here we go. We may also argue the following. The orthonormal set Fi is closed if and only if GFI equals 0 for all phi implies that G equals 0. Okay? Now that's a definition of a closed set. And now we're going to turn this into a theorem. The orthonormal set Fi in Hilbert space is complete if and only if it is closed. Okay? So we're defining a closed set, and then we're projecting a theorem that if the set you're working with is closed, then it also is complete. Okay? So let's prove it. Let's start with the simple one. Let's start with if complete, then closed. Okay? If complete, then closed. But we're actually going to prove it in the negatory fashion. That is, if not closed, then not complete. Hopefully you remember my comments from early on about the execution of proofs. If you want to prove this statement, then it's equivalent to prove this statement. Okay? So here we go. Assume a normalized function f of x, which is not 0. Okay? Such that fi f, which we'll call ci, which is the integral from a to b of fi star x f of x dx equals, I want this to not be closed. I'm specifying a non-zero function, so if I want it to not be closed, what should this be? Man, I'm going to pick a card. Not here. Madison. Madison. I know your dog's asleep, but come on, answer the question. Oh, that is a cat, sorry. From a distance, it looked like a dog. Madison, what's this got to be equal to? I know, it's got to be tough. I've suddenly drawn your attention to the lecture, which you're playing, and you're just sitting there. I think you're on, what's that video thing? TikTok? Yeah, am I on TikTok yet? I hope not. All right, if this set is not closed, and this is a non-zero function, what is this?
She doesn't have a mic, but
Oh.
I would say that it's not complete.
It's not complete if the inner product of the function with the set of orthonormal functions is 0. Yes. Okay, sorry, Madison, I didn't know your microphone wasn't working. You could have just used sign language. I speak sign language fluently. Kidding. Okay. Then, now we just want to show that this implies that the set is not complete. Okay? So here we go. Then the limit, as n goes to infinity, of the integral from a to b of f minus the sum from I equals 1 to n of ci fi squared dx, okay? If it were complete, what would this be equal to? If the set fi were complete, okay, I'm going to pick a card. I'm just going to pick a card token. Scott.
0.
0, thank you. You guys all know the answers, you're just not barking them out.
The answer is always 0.
Say again?
You gotta mix it up. The answer is always 0 for this class.
Earlier it was M.
Okay.
Earlier it was
Okay. So what is this equal to?
0.
No, it's equal to the inner product of f with f, right?
So what are the CI's equal to? In this assumption,
0.
the CI's are equal to 0. So this term is 0, So this simplifies to the limit as n goes to infinity of the integral of f squared dx.
So that
Okay.
breaks the theory that the answer to every question is 0.
What is this equal to?
One, because it's normal.
Yes, thank you. It's a normalized function.
Sorry, I can't really see the board.
Oh, it's okay. It's okay. This is not 0. So the space is not complete. Are we on board? We just proved that in the situation where it's not closed, that's when this is not 0, but this is 0, it is also not complete. Okay, this is in the mean convergence. All right? Whew, goodness. All right. That was the simple one. Now we're going to do the hard one. Which, yeah, it's got me nervous. I'm going to ask lots of questions. No,
Just make sure the answer is 0. We'll get it.
Okay, yeah. If the answer is A, then my question will be, what is A minus the n? Okay. All right, now we're going to do if closed, then complete. Okay, it's an if, so we also have to have it work the other way. But of course, we're going to do it this way. Not complete is not closed. Okay, here we go. Jeez. Assume an fx exists such that the magnitude squared is greater, okay, than the sum of these interproductive terms. Okay, remember, this is Bessel's inequality, but we're specifying that it's not equal, therefore it's incomplete. Okay? Now that is our starting point. Now, we can make a convergent sequence Gm of x with Gm of x being equal to the sum from n equals 1 to m of Cm Fn x. Okay? Now, GMX is a Cauchy sequence in Hilbert space, and Hilbert space is complete, so that means that this thing must converge to a function in Hilbert space, and we'll call it g of x. So this converges to some function g of x with expansion coefficients, which are the inner product of the set Fn with the actual function g. Okay? Now, these expansion coefficients are the same as these. All right? So what we can say is Fng, the inner product of Fn with g is the same as the inner product of Fn with f, which tells me that Fn times f, or the inner product of Fn with f minus g is equal to 0. So f minus g is orthogonal to all of the Fn. Okay?
I have a question.
Yeah.
to Fn inner product of F?
Is they're both equal to Cn?
They're both called Cn.
The book says, suppose two functions have the same coefficients. That's the way expansion coefficients, it just starts with that.
Yeah.
So it's define G and F as two different functions with the same coefficients, expansion coefficients. Interesting.
Oh,
How are they not just the same function?
yeah.
Wasn't G,
G is what this sequence converges to. I mean, we're going to argue whether F minus G is 0 or not in a minute.
Oh,
Okay,
okay.
but the question though is, before you've made that argument, how can you argue that the CNs are the same? No, actually, okay. It is not something to be proven, it is an assumption. Okay? That's an assumption that we're going to make. Which, of course, if you're making an assumption, there's nothing that will invalidate
Part
it.
of the assumptions, both
Huh?
those lines. Both those lines are part of the assumptions for this.
Yes.
So the point of this then is to prove that F minus G is equal to 0?
Well, we're going to figure that out in just a minute. Actually, what we're going to prove is that F minus G is greater than 0.
Okay.
Because remember, we
I
want
guess
to...
I'm just not following this process super well. How does that show us that if this is closed, then it's complete? How does that tie back into like the overall goal of what we're
We're
doing?
not. We're showing that if it's not complete, then it's not closed. So if it were closed, then F minus G would be 0. Okay? Because F minus G is orthogonal to all of the functions. And if the set is closed, then it's orthonormal to the set of functions. And it's not 0. Okay? But what we're showing is that an incomplete set is not closed.
Okay, one last question then.
Sure.
Sorry about this. How do we know that F minus G is orthonormal to all of the other functions in this set?
Because if we have the equivalence of these coefficients, Fng is equal to Fnf, then I can just use the algebraic properties of the inner product to move this to the other side of the equal sign, and then say Fn g minus f, or f minus g, it doesn't matter. This inner product is 0. That means that this is orthogonal to any of these.
Okay, so the thing that my initial question was about is then showing if they're orthogonal. Okay, I think I get it now. Thank you.
Okay, all right. Okay, here we go. So, obviously, as I just promised, if this is not 0, then it's not closed. So all we're going to do is show that this is not 0. Okay? So here we go. So consider,
It's not zero, it's key.
say it again?
It's not zero.
It's not, yeah, we're gonna prove that. Okay, yeah, all right.
Draw my card, I'm ready.
Okay, all right, I'll think of a really good question and then go with it. Hold on, I can't read my notes.
Never mind, don't draw my card.
Oh, yeah, that's just weird. Okay, this guy is greater than the magnitude of S minus F minus GM minus G minus GM for all M. And then as M goes to infinity, what we know is that the magnitude of G minus GM goes to 0, okay? Because remember, this sum converges to gx. So if you take the limit as n goes to infinity, these two become equal, so that's 0. So now what we have left is this term right here. And what we can say is f minus gm squared. And I'm going to analyze the square of this, but whatever we conclude about the square being greater than 0, we can conclude about the square root. This is equal to f minus the sum from n equals 1 to m of Cn Fn, quantity squared. And let me make some room. All right, here we go. So this is f minus sum n equals 1 to m Cn Fn, and it's the inner product of that with f minus sum from n equals 1 to m of Ck Fk, just giving that a different label. Now, just using the algebraic properties of inner products, this is f squared minus the inner product of f with the sum over m Ck Fk minus the inner product of the sum. No, hold on. K. I know. I'm being super lazy. Minus the sum of from n equals 1 to m of Cn star, or sorry, hold on, I'm skipping too far down. Cn Fn F plus the inner product of the sum from n equals 1 to m Cn, Fn, sum from k equals 1 to m of Ck Fk. Okay? Now if we expand this out even more, we're going to find the following. Now my summations and my constants can come outside of the inner product, and so this is going to give me sum from k equals 1 to m Ck, inner product of f with Fk, minus the sum over n equals 1 to m Cn star, inner product of Fn with F. And then we're going to have the sum over n equals 1 to m, sum over k equals 1 to m, Cn star, Ck, Fn, Fk. Whew. Okay. Now remember what we're trying to show. We're just trying to show that this thing is greater than 0. That's it. And if this is greater than 0, then it's not complete. Okay? All right. Well, let's see. This is equal to what? This is equal to
K some star.
yeah, so this is equal to CK star. Okay. This is equal to CK.
Or CN.
Sorry, CN. And then this guy, what is this equal to? That's delta NK, which degenerates this into a single sum. Okay? Clearly, we've got that. So we've got F squared minus the sum from K equals 1 to M FCK squared. Goodness, I didn't realize I was going over time. Okay?
Did we say earlier that F squared is greater than that sum?
Yes. Okay? But this is greater than 0. Okay? Which tells me that F minus GM is greater than 0 for all M. Okay? No, sorry, hold on. No, sorry. F minus G is greater than 0. Okay? So here we go. F minus G is not 0. Yet F minus G is orthogonal to all of the functions. Therefore, this set of functions is
Not close.
not closed. Okay? So Fi not being complete implies Fi isn't closed. Okay? Now I'll just make two quick comments and then we'll get the hell out of here and go on our fall break. These are both proven in the book. I'm not going to mess with it here, but here are two interesting results. We have two functions. And this is kind of ring and echo of some of the points that you were making when we were talking about these proofs. But the thing about proofs is you suppose something is true and then you later prove that it's not true. Okay, so that's why this is going to seem a little bit odd. If two functions, f and g, in Hilbert space have the same expansion coefficients, with respect to some orthonormal basis, Fi, that is, if Fif equals Fig, then the functions are the same. Okay? And B, any function in Hilbert space has a unique set of expansion coefficients with respect to any orthonormal basis. So if you have a function in your space and you pick a complete basis of orthonormal functions, that function is always going to have the same expansion coefficients. There's only one set of expansion coefficients that you can supply these orthonormal functions with in order to create the function. Okay? That's it. Let's get out of here.